Alright, welcome back, guys. We're going to be looking at this one section in Chapter 7. It's kind of an introduction to probability theory. Okay, and in my face-to-face classes, I always like to ask students or ask the class to give me like a definition of probability or what comes to mind when you hear that word probability. Okay. Because it's an entire field in and of itself in mathematics, probability theory. And probability theory is used a lot in statistics. In fact, it's really sort of the backbone of inferential statistics. So I would define probability as basically the likelihood that something will occur or not occur. Okay? It's trying to quantify the likelihood of something. Yeah, that's a pretty decent definition. And we're going to have some other definitions or some other terms here to learn. So within probability, guys, we're kind of concerned about think about horse racing, for example. You might be, let's say you're betting on the horses. You might be concerned with how probable is it that if I bet on this particular horse that I'll win, okay? And so there are probabilities assigned to those different outcomes, okay? So let's look at these two terms initially. So, well, actually, before we do that, let me just say a few things. Probability is behind everything in our lives. When you watch a weather forecast, there is probability behind that. Okay, probability is used in determining your rate or the premiums of insurance. Okay, it's based on the likelihood that you're going to get sick or that you're going to be involved in a car accident. Okay, so it's used, it's everywhere essentially. Okay, and we use probability, or we assign probability of to outcomes just intuitively. You might think about, okay, well, how likely is something to occur? And based on your intuition of the likelihood of that event occurring, you make other decisions accordingly. Okay? So anyway, all right, so an outcome is the most basic possible result of an observation or experiment. Okay? For example, if you toss two coins, and coins are used a lot in trying to explain or conceptualize probability theory. Coin flipping, also like cards, things of that nature, games of chance. If you toss two coins, one possible outcome would be that the first coin could land heads and then the second coin could land tails. Okay, that is one outcome. And then another possible outcome is that the first coin could be tails and the second coin could be heads. And there are other outcomes as well. As you guys know, first coin could be heads and the second could be heads, or the first coin could be tails and the second could be tails. Okay. So there's actually 4 outcomes when you flip two coins. Now, an event is broader. An event consists of one or more outcomes that share a property of interest. Okay, so in the context of this example, if the event is okay, so let's say we toss two coins and we count the number of heads. The outcomes heads and then tails and then heads, they both represent the same event. And the event is that you get exactly one head and one tail. Okay, There's two different ways to do that. So that particular event, that when you flip two coins, you'll get exactly one head, which means the other coin will be a tail, that can occur two possible ways. So you say that that one event is made up of two outcomes. Another example would be the event that you get two heads. Well, that particular event is only comprised of one outcome, because there's only one way to get two heads. First coin is a head, and the second coin is a head. Okay. And another event could be that you get zero heads, and that event can occur only one way as well, and that's if both coins are tails. Okay. Let me give you another example. So an event might be, another example of an event is that it rains over the weekend. And there are many different ways that can happen. Okay, it could rain on Saturday, that would be one outcome. Or it could rain on Sunday, that could be another outcome. Or it could rain on both days, both Saturday and Sunday, that could be another outcome. So that one event would be comprised of three different outcomes. And you could get even more specific with it. You could say, what's the probability that it rains tomorrow? Or the event is that it rains tomorrow. Well, that can occur in many different ways, because it could rain tomorrow at 12 o'clock. It could rain tomorrow at 5 o'clock. Okay, so the outcomes comprise the event, but typically the event is broader. All right, we'll see some more examples as we progress. Also, let me say a little bit about probability theory. It really began in the 1600s in Monaco, which is basically in France, okay, on the Mediterranean coast. And there were games of chance that were being played. And so to understand and begin to assign probabilities to the outcomes of these different games of chance led to the development of probability theory. Okay? And probability theory is used in these casinos. Basically, there were casinos back then. Those were some of the first casinos. And so if you've ever been to a casino or know much about casinos, you know there's a phrase that the house always wins, or in other words, the casino will always win. All that means is that on average, the casino will take in more than it pays out. Okay, that doesn't mean that you're never going to win, right? But on average, the casino has calculated ways such that it will win the majority of the time. Okay, because casinos are for-profit businesses. All right, so let's look at another example. Okay, so consider families with two children. So my family, for example, where my mother and father had myself and my sister. It says list all the possible outcomes for the birth order of boys and girls. Okay, if we are only interested in the total number of boys in the family, what are the possible events? Okay? So if I were just to list all the possible outcomes, then the first child could be a boy, and the second child could be a boy. Okay, that's one outcome. The first child could be a boy, and the second child could be a girl. Okay, or the first child could be a girl, and the second child could be a boy, or you could have two girls. Okay, so with a family that has exactly two children, these are all the possible outcomes. Okay. Any family of two that has two children, they're going to fall somewhere within one of these outcomes. Okay, and we'll talk later. Anyway, It says, if we're only interested in the total number of boys in the family, what are the possible events? Well, the events would be this, that there are 0 boys, that's one event, that there are exactly 1 boy, or that there are 2 boys. Okay? These are the different events. Now, this event right here is only comprised of this one outcome. Okay? That's the only way you can have 0 boys, is if both of your children are girls. But the second event right here, 1 boy, having 1 boy, there are actually 2 outcomes that fall underneath that comprise that one event. Because the order doesn't matter, okay? And then the event that you have 2 boys can only occur one way. Or in other words, there's only one outcome that comprises this event. So actually having 1 boy and 1 girl is the most likely event to occur, okay? Because it can occur 2 different ways. And so that's why if you were to sample a bunch of families, you would find that on average there would be more families that have exactly 1 boy and 1 girl than 0 boys or both boys. Okay. Right. So this just repeats what we stated. Okay, so how do we express probability? Well, I said earlier that the probability is the likelihood of something happening or not happening. Think about weather. When you look at the weather forecast, they give a probability to the likelihood that it's going to rain on a particular day. And that's typically given as a percentage, like 20%. There's a 20% chance of rain tomorrow. Okay? So the likelihood of an event occurring has to be quantified. And this can be done either using percentages, anywhere from 0% to 100%. It can be done using decimals, so from 0 all the way to 1. Because remember, percentages, so 75%, for example, is the same as 0.75 as a decimal. Okay? And then probabilities can also be expressed as fractions. So you'll know this if you've ever done any horse racing, betting on horse racing. So your horse, the odds are a little bit different, but they basically are just another way of assigning probability. Okay? The odds of your horse winning might be 5 to 2 or something like that. Okay, 3 to 4. But anyway, so typically we use a capital P. We'll use a capital P, and then in parentheses we'll have the event that we're considering. So when you see something like this, and lots of times events will be represented using a capital letter, so like capital A. So if you were to see this is notation that means the probability of event A occurring. Okay? So it's almost sort of like a function in a sense. If you remember anything from your algebra classes, it's sort of like function notation. The probability of some event occurring is equal to, and then we're going to be focusing on trying to figure out what is that probability. Okay? So the probabilities can range anywhere from 0 to 1 in decimals. Okay? Now in percentages, it would be 0% all the way to 100%. Okay? And so we have a scale right here. We say that an event that has a probability of 0, it means that event cannot occur. It's impossible. Okay. I'll give you an example. The probability that I both pass and fail this class is 0, because it's not possible to both pass and fail a class. Those are what we call mutually exclusive events. They both cannot occur. Only one will occur. Okay. Now, I'll give you an example of an event that's certain to occur that would have a probability of 1. And that would be, let's see, the event that I either pass or fail this class. Notice I use the word or. So, or means only one of the two things has to happen. So, the probability that you either pass or fail is 1. It's certain because you're either going to pass the class or you're going to fail the class. Okay? Think about weather too. Sometimes the weatherman will give the probability of rain as 100% if you keep up with the weather forecast. That means they are certain that it's going to rain. Okay? And sometimes you'll see they'll also assign the probability of rain as real low, like 10% or even 0%, in which case they just don't put any rain chance in the forecast. Okay. And then, so, you know, right here you would have 25% or 0.25. So an event that has a probability of 0.25 is said to be pretty unlikely to occur. An event that has a 50% chance or 0.5% probability is just as likely to occur as it is not to occur. And then an event that has a probability of around 0.75 or 0.8, we would say that's pretty likely. Okay. All right, let's continue. So there's different methods that we can use, or different lenses with which to view, to go about trying to calculate probabilities for certain events. And the first one we're going to talk about is this theoretical method for equally likely outcomes. Okay? So if you're considering an event in which all of the outcomes are equally likely, then you can use this theoretical approach. Okay? And the way it goes is this. Step 1 would be to count the total possible number of outcomes. Okay, so how many ways could this event occur? What are all the different outcomes? And then among all those possible outcomes, count the number of ways that the event of interest can occur. Okay? This will make more sense here in a minute. And then step number 3 is determine the probability of A. So in other words, you're going to end up with a fraction. So the probability of A will be equal to the number of ways that A can occur divided by the total number of outcomes. So think back to that family of two children. The probability that a family that has 2 kids will have 1 boy is 2 out of 4. The reason is because if we scroll back up here, the total number of outcomes, if you have 2 children, is 4. Okay? But there are only 2 ways that if you have 2 children, you'll get just 1 boy. Okay? It's this one here, and then this one here. Okay? So there are 2 possible ways that you can have just 1 boy, but there's a total of 4 possible outcomes there. So we would say that the probability that if you have 2 kids, you're going to have 1 boy and 1 girl is 2 out of 4, which is the same as 50%, or 0.5. Okay? The probability that you have 0 boys, or in other words, all girls, would be 1 out of 4, because there is only one way that you could have 0 boys, and that's if you had 2 girls. And then, furthermore, the probability that you have exactly 2 boys, they're both boys, is 1 out of 4. So you'll notice the denominator, 4, stays the same in all these examples. Okay, because it's the total number of outcomes. Alright, so now let's think about coins and dice. Dice are used a lot in examples as well. Okay, so what we want to do is apply the theoretical method to find the probability of A, exactly 1 head, getting exactly 1 head when you toss 2 coins. Okay, so that's the event. And I can even write it like this. The probability of one head, okay, is equal to, well, first think about all the outcomes. So if you toss two coins, we did this earlier. These are all the outcomes right here. I'm going to zoom in. This is a visual. This is an outcome in which you get two tails, okay, which means 0 heads. These are the events down here. And these are the outcomes up here. Another outcome would be that the first coin is a tail and the second coin is a head. The third outcome is that the first coin is a head and the second one a tail. But look, both of these two outcomes comprise this one event, that you get one head. And then lastly, the fourth outcome is that both coins are heads, okay? And so the probability that you get exactly one head, well, there's two ways that that can occur. There are two outcomes, okay? Out of a total of 4 outcomes, because there's 4 outcomes when you, 4 possibilities when you toss two coins. So 2 out of 4 simplifies to the fraction 1/2. Okay, so that's why the answer is 1/2. Or in other words, you have a 50% chance that if you toss 2 coins, that one will be a head and one will be a tail. Or in other words, that you'll get exactly one head. Okay. Now let's think about a die. Die is singular of dice. So what's the probability of getting a 3 when you roll a 6-sided die? So we would express it like this: probability of getting a 3. Okay. Well, think about all the total outcomes when you roll a 6-sided die. Well, because there's 6 sides, there's 6 outcomes. And the outcomes would be anywhere from a 1 to a 2, all the way to a 6. Okay? But there's only one of these outcomes that produces a 3. So we would say the probability is 1 out of 6. Okay, so some of this stuff you guys already kind of know intuitively. Okay? It's just, sometimes this is the process of mathematically formalizing it that possibly makes it a little bit confusing. Alright, now cards are commonly used in probability examples, okay, in practicing with probability. And so I included a graphic of a deck of cards here. I've done this because in the past I've had students that weren't familiar with a deck of cards. Okay, and so let's talk about this for a minute. With a deck of cards, you have 4 suits. Okay, the suit is the shape. So like this is a heart. This is what we call a spade. This is what we call a club. It looks like a clover. And then this one is a diamond. Okay, so there's 4 suits in a deck of cards. And then in each suit, the cards range from an ace, which in some card games can count as a 1, can have a value of 1. And then a 2, a 3, a 4, all the way up to 10. And then these cards up here, these are called face cards. And the J is for Jack, the Q is for Queen, and the K is for Queen. Okay. Now in each suit, there's 13 cards. So 13, 13, 13, and 13 makes a total of 52 cards. Okay, so there's 52 cards in a standard deck of cards. And then one last thing characteristic is 2 of the suits are black. The suit of clubs and spades are your black cards, and then the suits of hearts and diamonds are your red cards. Okay? So half of your cards are black and the other half are red. Alright, so knowing that, this just goes over what I just explained. Knowing that, we can figure out
some of these probabilities. So think about having a deck of cards and just randomly drawing one card. Okay? And so what would be the probability that that card ends up being a spade? Well, the spades are all of these cards. And if you remember, there are 13 of them. Okay? So there's 13 spades, so that will be the numerator. And then the total number of cards, or in other words, the total number of outcomes is 52, because there's a total of 52 cards. So 13 out of 52, that's the probability that if you randomly draw a card from a standard deck, that it's going to be a spade. Now, when you're using fractions, we want to make sure these are simplified. And 13 out of 52 can be simplified because you can divide both of these by 13. 13 goes into 13 one time, 13 goes into 52 4 times, and so the probability of drawing a spade is 1/4. You can think about it this way too. A spade consists of one whole suit, and there's a total of 4 suits, so 1 out of 4. I'll also express this as a decimal. As a decimal, it would be 0.25. Remember, to find the decimal, you just divide 1 by 4. And then as a percent, you multiply by 100 and you get 25%. So you have a 25% chance of drawing a spade. Okay? Alright, I think we'll talk about this next slide rather. And then we'll stop this part 1 video. Okay, so outcomes and events again. So assuming an equal chance of having a boy or a girl at birth, and that's what we typically assume. You know, you're just as likely to have a boy as you are to have a girl. Although from a biological perspective, I don't know if that's actually true. I want to say that that's not actually true. That one sex is actually slightly more likely. Seems like I read that in the past, but I could be imagining something. Okay, so what is the probability of having 2 girls and 2 boys in a family of 4 children? Okay, so the event is, you could write it, you could express it like this: the probability of 2 girls and 2 boys. Okay. But there's an easier way to express that event. You could just write it like this. Because if you have 2 girls, that means the other 2 children have to be boys. Okay. So what I've done in this table here is I've listed all the possible outcomes. Okay, so the possible outcomes are these right here: that all 4 could be girls, or that the first 3 could be girls and the last one a boy, or that the first 2 could be girls and the third child a boy, or that the first child could be a girl, the second a boy, and then the rest girls, or the first child could be a boy and the rest girls. Now all these 4 outcomes here comprise this one event, that you have 1 boy and 3 girls. See, that can happen 4 different ways when you take into account order. These are the events over here on the left-hand side, by the way. Now, all the possible ways that you could have exactly 2 girls and 2 boys, well, they're all listed right here. And there's 6 possible ways that could happen. And then all the possible ways that you could have 1 girl and 1 boy, or excuse me, one girl and 3 boys, so this is just kind of the reverse of this up here. There's 4 different ways that could happen. And then finally, probability, or the number of outcomes that comprise this event, that you have 4 boys, well, there's only 1 way that can happen. Okay. So to find the probability that you have 2 girls, you're going to look in this row right here. Having 2 girls can occur 6 different ways. In other words, there's 6 outcomes that comprise that event. Okay. Now, when you have 4 children, what's the total number of outcomes? Well, we'd have to count up all these. There's actually a total of 16. Okay, so it's 6 out of 16, which can be reduced. I'm going to put this up here, 16 possible outcomes. 6 out of 16, if you divide both of these by 2, that'll reduce this fraction down to 3/8. Okay? And as a decimal, that would become 0.375, or as a percent, it would be 37.5%. Okay? But that, again, that's the most likely outcome, is that you have half and half. You have 2 boys and 2 girls. It's less likely that you have just 1 boy and 3 girls, or 1 girl and 3 boys, and it's even less likely to have all boys or all girls. So if you know somebody that had 4 children and they were all girls, or they were all boys, that's a very unlikely probability. In fact, the probability is 1 out of 16, right? Okay, so even though the probability is low, that if you have 4 kids, they're all going to be boys, doesn't mean it's impossible, because you probably know people. Okay, it just means that it's less likely. You're more likely to get some kind of mixture. All right, guys. Well, this is a good place to stop, because so we've looked at using the theoretical approach in calculating probabilities. This approach is used when every outcome is just as likely as the other outcome. Okay? And what I mean by this is that when you're having that next kid, you assume the likelihood that you're going to have either a boy or a girl is the same. It's like the flip of a coin. Okay. And so the next lens through which we're going to view probability is this relative frequency. And this basically looks at determining probability based on what's happened in the past. Okay, so this is used a lot in assigning probabilities to, like, developing diseases and making predictions about the stock market and stuff like that. You're looking at past data, and you're looking to see how likely that event will occur, how often that event occurred in the past, and you're using that to make a prediction about the probability of the event occurring in the future. Okay? So we'll look at this one in video 2.